Welcome back to Pixel Perception. Last episode we covered the three holy pillars: reliability, scalability, and maintainability. Today we go one level deeper and tackle a question that causes more debates in engineering teams than almost anything else.
Oh, I already know what it is: SQL versus NoSQL. Right. I have sat through that argument at literally every company I have ever worked at. Nobody ever actually wins it.
You are not wrong, Leo. But here is the thing. Most people argue about SQL versus NoSQL without actually understanding why each one was designed the way it was. Today we fix that completely. By the end of this episode, you will have a real, principled answer, not just the classic engineer cop-out of "it depends."
Okay. I will admit you always make me feel like I know about 30% less than I think I do. Which is somehow a compliment coming from you. Let us go.
Before we pick sides in the SQL versus NoSQL debate, we need to understand what a data model actually is and why it is the most important decision you will make when designing a system.
Before we argue about which database to use, what exactly is a data model? It sounds like a very official, scary term.
It is the most important decision you make when building any system, and most developers make it almost by accident, without really thinking about it. A data model is simply the way you choose to represent real-world information inside your software. It answers fundamental questions. How do we organize the data? How do different things relate to each other? And most importantly, what questions can we ask of the data efficiently?
And why does this choice matter so much? Can we not just store data somewhere and query it somehow?
Because the model you pick deeply shapes what kinds of queries are fast versus impossibly slow. It shapes whether your schema can evolve over time without breaking everything. It shapes how your developers think about the problem. Kleppmann says it beautifully: data models are so important because they not only affect how software is written, but how we think about the problem we are solving. Your mental model of the data becomes your mental model of the entire system. Let us meet the reigning champion. The model that has dominated computing for 50 years. The relational model. The dominant data model for the last 50 years by an absolutely massive margin is the relational model. And the query language built on top of it is SQL. It was proposed by Edgar Codd at IBM in 1970. And his idea was genuinely revolutionary for the time, not just a small improvement, but a complete rethinking of how databases should work.
What made it so revolutionary? Tables and rows seem like a pretty obvious idea in hindsight. Like, of course you put data in rows.
Before Codd, every database was a nightmare. You had to know the exact physical layout of data on disk to query it. The database was tightly coupled to the specific application code that wrote it. Codd's insight was breathtaking. Separate the logical model from the physical storage. You describe what data you want, not how to find it. The database engine figures out the how. That abstraction called data independence is the core reason SQL is still alive and dominant 50 years later.
So in a relational database, Everything lives in tables, rows and columns. You connect tables together using foreign keys and join operations. What are the main strengths that kept the relational model king for 5 entire decades?
3 massive strengths that are genuinely hard to beat. First, it handles many-to-many relationships between different types of entities absolutely beautifully through joins. One user can have many orders. One order can have many products. One product can belong to many categories. Relational handles all of this naturally and efficiently. Second, the query optimizer automatically picks the best execution plan. So you write clean declarative queries and the database does the heavy lifting. Third, decades of battle-tested reliability. Banks, hospitals, airlines, governments, the entire world runs on relational databases. But the relational model has a frustrating friction point that motivated an entire new category of databases. It is called the Impedance mismatch.
Okay, so SQL sounds genuinely perfect. But if it is so great, why did NoSQL even appear? Someone must have found a real, painful problem with the relational model.
There is a very real friction point called the Impedance mismatch. It sounds deeply technical, but the idea is simple enough that a teenager can understand it. Modern application code is written in object-oriented languages: Python, Java, JavaScript. Your code works with objects. A user object has a name, an email, a list of address objects, a list of job history objects, a list of skills. But a relational database stores everything in flat, two-dimensional tables. Those two worlds do not naturally fit together.
Oh. That is why every project uses an ORM like Hibernate or SQL Alchemy to translate between the objects in your code and the flat tables in the database.
Exactly right. ORMs are literally translation layers that exist purely because of the Impedance mismatch. They are a patch for a structural incompatibility. And they introduce their own complexity, the infamous N+1 query problem, where loading a list of objects triggers hundreds of separate database queries. Unexpected lazy loading surprises. Performance cliffs in production that are hard to diagnose. It is a constant, low-level tax that every team using a relational database pays every single day. And this accumulated frustration is precisely what motivated the NoSQL movement to emerge. Quiz 1. Let us make sure the relational model and the Impedance mismatch are locked in before we introduce the challenger.
Alright, before we introduce the challenger, let us make sure the relational model and the Impedance mismatch are locked in. Read this question carefully, the wording matters here.
Perfect. The Impedance mismatch is the structural gap between how application code represents data as objects and how relational databases store it as flat rows and tables. ORMs exist purely to bridge this gap. Now for the challenger. In the early 2000s, a rebellion was brewing in the engineering community. Its name was NoSQL. The term NoSQL first appeared publicly around 2009, and it was never actually a coherent technical movement. It was more of a rebellion hashtag. A label for a conference meetup of engineers who were frustrated with relational databases for specific use cases. The original intent was not only SQL meaning. Relational databases are great, but maybe they are not the right tool for every single job.
So what specific problems were engineers running into with SQL that pushed them to build something completely different from scratch?
3 genuine, painful problems. First, at massive internet scale. Horizontal scaling of relational databases is genuinely difficult and fragile. Sharding a SQL database across dozens of machines requires enormous engineering effort and introduces complex consistency challenges. Second, the Impedance mismatch. We just discussed the constant friction between objects and tables. Third, some applications have extremely flexible, rapidly changing data structures. A user profile today might have 10 fields. Next year it needs 200. Relational schemas are rigid. Every structural change requires a migration that can lock your entire table for hours on a dataset with hundreds of millions of rows.
So NoSQL was not born from someone just wanting to be different or trendy. It was born from real engineering pain that relational databases genuinely could not solve efficiently. Got it? So what does a document database actually look like in practice?
The most popular category of NoSQL databases is the document database. And its killer feature is so elegant it almost feels obvious in hindsight. A document database, MongoDB, is the most well-known example. But CouchDB is another, stores data as self-contained documents. Think of a document as simply a JSON object. Instead of spreading a user's data across 5 different tables connected by foreign keys, you store the entire username, email, job history, addresses, preferences, everything as one single JSON document.
Oh. So it completely solves the impedance mismatch. The document already looks exactly like an object in your application code. You load it and it is already the shape your code expects.
That is the killer feature. Your LinkedIn profile, for example, is a perfect document. One person, all their data in one place. Name, location, a summary, education history as an array of objects, work experience as an array of objects, skills as an array of strings. One single read from the database returns everything you need to render the entire profile page. With a relational database, you would need 4 to 6 separate join operations across multiple tables to assemble the exact same data.
I genuinely love that. But there has to be a catch, otherwise everyone would have switched to MongoDB years ago and we would not still be having the debate.
And here is the catch. Document databases have a specific weakness that relational databases handle naturally and elegantly. You are right to be suspicious, Leo. The catch is many-to-many relationships between different types of entities. Document databases shine brilliantly when your data is naturally self-contained, like a user profile, a blog post, or a product page. But the moment you need to represent rich connections between many different types of entities, documents start to create serious problems.
Can you give me a very concrete example of exactly where it breaks down?
Absolutely. Think about a job listing on LinkedIn. The listing needs to reference a company, its name, logo, description, founding date. But that company information is shared across potentially thousands of different job listings all at the same time. If you embed the full company details inside every single job listing document, you now have thousands of exact copies of the same company data scattered across the database. When the company changes its logo or updates its description, you have to find and update thousands of separate documents. This is called data denormalization, and it creates genuinely serious data consistency problems.
So document databases are great for one-to-many relationships within a single entity, but they struggle badly with many-to-many relationships between entities. And the relational model is exactly the opposite. It handles cross-entity relationships beautifully through foreign keys and joins, but struggles with flexible nested structures.
That is the cleanest summary of the trade-off I have ever heard stated out loud. Honestly, Leo, sometimes you surprise me. Yes, that is exactly it. And that complementary trade-off explains precisely why the SQL versus NoSQL debate never ends. Both models are genuinely better than the other for specific, different use cases. Quiz 2. The most important trade-off in the chapter. Think carefully before clicking.
Alright, let us test whether you truly absorbed the most important trade-off we just covered. This exact question comes up in every senior engineering interview I have ever heard about. Take your time.
Yes. This is a perfect one-to-many use case within a single entity. Everything about one patient lives together. A document database stores it all in one JSON document, one read. Everything you need. Elegant. Now, one of the most useful and underappreciated distinctions in the entire chapter. Schema-on-Read versus Schema-on-Write. Here is one of the most useful and underappreciated distinctions in the entire chapter. Relational databases enforce Schema-on-Write, meaning the structure of your data is strictly defined before you write a single row. Every record in the user's table must have exactly these columns, these data types, these constraints. The database will physically reject any data that does not conform to the defined schema.
And document databases do the opposite, they just accept anything you send them.
They use Schema-on-Read. The database accepts any JSON document you throw at it, regardless of structure. The schema only exists implicitly in your application code, which interprets and validates the document when it reads it. It is exactly analogous to the difference between a statically typed language like Java, which catches type errors at compile time before the program even runs, versus a dynamically typed language like Python, which only discovers type errors at runtime when that specific line of code is executed.
So Schema-on-Read is more flexible, great for rapidly changing requirements where you need to evolve the data structure frequently. But Schema-on-Write is safer, it catches data quality problems before they get into the database where they can corrupt your entire data set.
Perfectly put. Schema-on-Read is fantastic when your data is heterogeneous. Different documents might have completely different shapes because different users have opted into different features. Schema-on-Write is fantastic when you need absolute data integrity guarantees that cannot be violated under any circumstances, like in financial systems where every transaction must have exactly the required fields with exactly the right types. Or it gets rejected before it ever touches the database. Quiz 3. This one catches people off guard. Read the scenario carefully before you decide. This one catches people off guard because the answer feels obvious but the reasoning matters enormously. Think through the specific requirements before clicking. Absolutely right. In banking, data integrity is non-negotiable. Schema-on-Write enforces that every single transaction has exactly the required fields before it's accepted. Malformed data is rejected immediately before it can cause a financial discrepancy. And now the third major data model, and arguably the most fascinating one. Graph databases. We have covered relational and document models thoroughly. Now let us talk about the third major category, graph databases. These are designed for a completely different kind of problem. Data where the relationships between things are just as important as the things themselves, or even more important.
What kind of real-world data looks like that? Give me some concrete examples.
Think about Facebook's social graph, billions of users connected to billions of other users through friendships, group memberships, page likes, and event attendance. Or LinkedIn's professional graph, people connected to companies, schools, skills, and other people. Or the entire internet itself, billions of pages connected to billions of other pages through hyperlinks. Or fraud detection, bank accounts connected to transactions connected to devices connected to IP addresses and phone numbers. In all of these use cases, the connections between entities are the core data that makes the system valuable, not an afterthought.
Could you technically model a social network in a relational database? Like using a friendship table with 2 foreign keys to the user's table.
Yes. You can model connected data in SQL, but watch what happens when you try to query it deeply. This is where relational databases start showing their limits. You can absolutely model a social network in SQL, but it becomes extremely painful very quickly for anything beyond surface-level queries. Imagine you want to answer: find all friends of friends of friends of Alice who currently work at Google. In SQL, that requires self-joining the friends table 3 separate times, with increasingly complex query logic. If you want 6 degrees of separation, which is what LinkedIn actually computes, you are writing a monstrous multi-level join query that the database optimizer cannot even efficiently plan.
But in a graph database, traversing through relationships is literally the native, most optimized operation it was specifically designed for.
Exactly. In Neo4j, the most popular graph database, you write that same query in a language called Cipher. And it reads almost exactly like plain English. You write: find a path from Alice through knows relationships 3 steps deep to anyone who works at Google. The graph database traverses those connections natively, following pointers directly in memory without expensive join operations. A query that would take multiple seconds in SQL executes in single-digit milliseconds on a properly indexed graph database.
Okay, I have to say that cipher query pattern is shockingly readable. I actually understood the graph traversal on the first pass, which almost never happens with deeply nested SQL joins. This is kind of beautiful.
Quiz 4. Graph databases. Which real-world problem is graph databases specifically built to solve? Think about what graph databases are uniquely and specifically built to do and which real-world problem from the answer options matches that strength most naturally. Take your time on this one. Yes. Fraud detection is a perfect graph use case. A fraudster reuses the same device, IP address, or email across multiple fake accounts. By modeling accounts, devices, and IPs as nodes and detecting shared connections, graph traversal catches patterns that would require impossibly complex SQL queries. Now let us zoom out and talk about query languages themselves. How you ask a database for data is just as important as how you store it. Now let us talk about query languages because the way you ask a database for data is just as architecturally important as how you store it. There are two fundamentally different philosophies for querying any system: declarative and imperative.
I have heard those terms in programming discussions, but I have never had the distinction explained to me clearly. Can you give me a concrete side-by-side comparison?
Here is the most concrete comparison I can give you. Imagine you want to retrieve all users who are over 21 years old. The imperative approach. You write a for loop that manually iterates through every single user record in memory, checks if their age field is greater than 21, and adds them to a result array one by one. You are describing the exact mechanical steps how to get the answer. The declarative approach. You write select star from users where age greater than 21. You describe what you want, the database engine decides how to find it most efficiently.
And declarative is better because the database can automatically use indexes, choose between different execution strategies, distribute the work across multiple CPU cores, and potentially parallelize things that you would have to hand code yourself in an imperative approach.
That is exactly right, and here is the deeper insight that Kleppmann highlights. Declarative languages also hide their implementation details entirely. When the database team ships an improved query optimizer next year, your SQL queries automatically get faster without you changing a single line of your application code. The abstraction keeps giving you free performance improvements over time, indefinitely. This is one of the primary reasons SQL has remained so powerful and relevant for 50 years while most other software technologies from that era are long forgotten. Quiz 5. The declarative versus imperative distinction. What is the real advantage?
Okay, this one is mine to ask. I love this distinction and Aria. Honestly, that loop analogy finally made it click for me in a way textbooks never did. Let us see if everyone else gets the core insight here.
Exactly. You specify what you want, and the database engine decides how to fetch it most efficiently. This means the optimizer can use indexes, parallelize operations, and improve automatically over time without you changing your queries at all. That's the real magic of SQL. Now let us put everything together into a practical decision framework. This is what you actually use when choosing a data model for a real system. Alright. Let me give you the complete practical decision framework that Kleppmann builds across this entire chapter. This is what you actually use in the real world and in interviews when choosing a data model for a new system.
Finally, a framework I can actually use in an interview without just saying it depends and hoping the interviewer moves on.
Here it is. Choose the relational model when you have many-to-many relationships between different entity types. When you need strong data consistency guarantees. When your data structure is stable and well-defined. And when you need complex joins and aggregate computations. Choose the document model when your data is naturally self-contained with one-to-many relationships within a single entity. When your schema needs to evolve rapidly and flexibly. And when most queries read the full document rather than slices across many documents. Choose the graph model when relationships between entities are the core of your data. When you need to traverse connections of unknown or variable depth efficiently. And when your use case involves social networks, recommendations, knowledge graphs, or fraud detection. And now for the reality check. What do real companies at massive scale actually use in production?
Okay, theory is great, but what do actual big technology companies use in production? Because I suspect the real answer is a lot messy than pick one model and commit to it forever.
You are suspecting exactly correctly, and this is something that most textbooks gloss over because it does not make for clean chapter summaries. Real production systems at massive scale almost never use just one data model for the entire product. They use multiple different database models for different parts of the same application. This approach is called polyglot persistence, choosing the right database type for each specific job, rather than forcing one database to do everything.
Give me some concrete real-world examples of how major companies actually do this.
Here are real examples. LinkedIn uses a graph database specifically for the social connection graph, the people you may know feature, and a relational database for core user and job data. Airbnb uses PostgreSQL as the primary relational store for bookings and user data. Elasticsearch as a document store for property search. And Redis as an in-memory cache for sessions and frequently accessed data. Uber uses MySQL for trip data and driver profiles. And a separate graph-based system for routing and real-time mapping. The pattern across all of them is identical. Match each data model to the specific query patterns and access patterns it was architecturally designed to serve. Final quiz. This is the hardest one. It tests whether you can apply everything together in a realistic design scenario. This is the final quiz and the hardest one. It tests whether you can apply everything we covered today together in a realistic design scenario. This is exactly the type of architecture question you will face in a staff-level system design interview. Think it all the way through before clicking. This is the polyglot persistence answer, and it's the right one. Relational for songs and playlists handles many-to-many cleanly. A graph database for the recommendation engine handles the users who listened to X also listened to Y traversal natively and at speed. Using the right tool for each job is what senior engineers do. Let me give you the complete mental model from Chapter 2, the 3 things you now understand that most developers do not think about precisely. Let me lock in the complete mental model from Chapter 2. 3 things you now understand that most developers do not think about precisely, even experienced ones.
Go for it. I genuinely feel like a different engineer after this chapter. Which is slightly annoying because now I have to go back and rethink some architecture decisions I made at my last company.
First, your data model is not just a storage decision. It fundamentally shapes how you think about the problem and determines which queries are fast versus slow for the lifetime of the system. Second, relational, document, and graph models each have a specific sweet spot. Relational wins on complex cross-entity relationships and consistency. Document wins on self-contained flexible entities. Graph wins when relationships are the primary data. Third, in the real world, the most sophisticated systems use multiple data models together called polyglot persistence, choosing exactly the right database for each specific job. Coming up in episode 3, we go inside the database itself and answer a question most developers have never thought to ask. In our next episode, we go deep inside the database itself. Chapter 3 is called Storage and Retrieval, and it answers a question that most developers have genuinely never thought to ask. When you write a row to a database, where does it actually go physically? How does the database find it again among billions of other rows in under 100 milliseconds?
I will be completely honest, I have been treating databases as black boxes my entire career. I write SQL. Data goes in. Data comes out. I have never once thought about what happens in between.
Most people do. And after Chapter 3, you will never think of a database as a black box again. We are going to build a tiny but real functioning database from scratch using just 2 shell script commands to really physically understand what an index is. Then we go deep on the 2 dominant storage engine architectures, B trees, which power PostgreSQL and MySQL and virtually every traditional relational database, and LSM trees, which power Cassandra, RocksDB, and LevelDB, and you will understand precisely why each one was invented and when one dramatically beats the other.
Building a real database in 2 shell commands. Okay, now I am actually excited. Subscribe and hit the bell, do not miss that episode. It genuinely sounds wild. See you in episode 3.
If Chapter 2 helped you finally understand the SQL versus NoSQL debate at a real, principled level, not just as a vague feeling but as a concrete decision framework, please hit like. It takes 1 second and it tells YouTube that this kind of honest, deep technical content is worth sharing with more engineers and students who need it.
And subscribe. We have storage engines, distributed replication, consensus algorithms, batch processing with Spark, stream processing with Kafka, all coming in this series. Every single episode is built the same way. Visual, interactive, honest about the trade-offs, and designed to make you think differently. You genuinely do not want to miss any of them.
And share this video with one person, one friend, one colleague, one study partner who is preparing for system design interviews or who just wants to finally understand what database they are using and why they chose it. This is Pixel Perception, and we will absolutely see you in episode 3. Congratulations! You have completed episode 2 of the Pixel Perception System Design series. See you in chapter 3.